Okay, welcome back everyone. So in this video here, we're going to start talking about uh, factors that contribute to the importance of resonance forms. You know, how do we assess the relative stabilities of various resonance forms? You know, how do we know when we draw several resonance forms for a given structure, how do we know which one's a major contributor to that resonance and which one's a minor contributor? Okay, so before we go and do some examples, let's lay down ground rules here. So the first thing that we want to keep in mind is structures or resonance forms with complete octets are significant contributors. Second thing is fewer formal charges. Okay, so if we can draw resonance forms that have fewer formal charges compared to another resonance form which has more formal charges, then the one with fewer formal charges is significant, is a major contributor. And third, when possible, that means other factors are taken care of. Read that as 1 and 2 if you've drawn resonance structures with complete octets and plus fewer formal charges. If the negative charge is on a more electronegative element. Okay, so I think these are the main ones that we should focus on. Most important one, I would say, is getting complete octets, you know, and then minimizing the number of, not minimizing, but the one with a fewer number of formal charges. And then finally, if possible, if you can put, if there is a if there is a resonance form where the negative charge is actually on a more electronegative element, then that resonance form's going to be a major contributor. Okay, so let's examine let's look at a few examples, you know, which sort of show us this, you know. So let's draw some resonance forms here. So let's say we have a resonance form where we have I want to draw something else. Okay, let's say that's a molecular species we have. Okay, so we have a carbon with we have a methyl CH3 connected to a carbon, which has a positive charge to it, and attached to it there are 2 oxygen atoms with negative charges on them. And so to draw a resonance form of this given species or given structure, we have to go back to our criteria. So if you think about it, this would fall into the criteria where we have a lone pair next to a carbon with a positive charge, a lone pair next to a carbon with a positive charge. Either one is fine. Okay, so and what we do in that case, when you have a lone pair next to a carbon with a positive charge, is we actually take the lone pair and drop it to the space between the 2 atoms. So lone pair and drop it to the space between that oxygen and the carbon with the positive charge. We could have as well used this lone pair. Either way, this would have been fine because both oxygens are equivalent here. Okay, so we take one of the lone pairs and drop it down. And so we will get a structure where now there should be a double bond between that carbon and oxygen. This oxygen should now have 2 lone pairs to it, and then oxygen with 3 lone pairs and a negative charge. Okay, so that would be a resonance form for this given structure. So these are both resonance forms. We can enclose these in square brackets. Now, if you compare the 2 resonance forms, I think we can hit upon 2 of the points here. If you look at the first resonance form here, oxygen has a complete octet, 2, 4, 6 plus 2, 8 electrons. This oxygen has a complete octet, 2, 4, 6, and 8 electrons. But the carbon here has a positive charge on it. It has 3 bonds to it, so it only has 6 electrons. So it has an incomplete octet. It is missing some electrons. In the other resonance form, when you look at it, the oxygen at the top has 2, 4, 6, and 8 electrons, complete octet. This oxygen has a complete octet, 2, 4, 6, and 8. And the carbon now has 4 bonds to it, which all bring 2 electrons each. And so there are 8 electrons. So what you notice is this carbon here has a complete octet, and so is every other atom, whereas here we had an incomplete octet. Okay, so based on those 2, we can say that between these 2 resonance forms, this is going to be a major contributor to the resonance hybrid, okay, or in terms of what the structure would look like. Okay, so it's a major contributor. Now, similarly, if you look at formal charges, what you notice is in the first structure here, we have 3 formal charges. In the second structure, there's only 1 formal charge. So it actually hits upon that point also, that we've minimized the number of formal charges in this resonance form. So that would also make it a major contributor. Okay, so I basically chose an example where we have like both, but let's look at another example maybe. Okay, so let's look at another example where we can talk about octets, and then we can talk about formal charges. Okay, so let's say we have an example where we have a positive charge here, double bond. We have an oxygen with a negative charge. Also treat these as examples for, how would you do resonance. Okay, so you have a molecule or you have a structure for which you have to construct some resonance forms. So what you can notice is this actually has, it kind of meets 2 criteria based on what we've discussed. We have a positive charge at an allelic position because this carbon is allelic. We also have a lone pair at an allelic position. Okay, so there are 2 criteria that this molecule meets, but doesn't matter, we can pick either one and start from there. So what we'll do is let's start with the positive charge at the allelic position, okay, and then see what happens. Okay, so if we have a carbon at an allelic position, or any other atom for that matter, with a positive charge at an allelic position, the way we start resonance is we'll take the pi bond here and move it to the space between those 2 carbons there. Okay, this would give us a resonance form where we have a double bond between these 2 carbons now, single bond here, single bond to the oxygen, and then we have the oxygen there, lone pair. Okay, and when we do this arrow push, the positive charge also moves. So, or the positive charge now, the formal charge is now on this carbon that's next to the oxygen atom. Okay, so these are both resonance forms. So I took the electron pair, the pi bond here and moved it to the space between these two carbon atoms. And remember that the two electrons here, one of them was contributed by this carbon and the other one was contributed by the carbon at the bottom here. That's why when we move both electrons, the carbon here at the bottom should get a positive charge. The carbon at the top, it still gets to keep its electrons, so no formal charge for that. So you have positive charge over there. So now we have a carbon with a positive charge with a lone pair next to it. And so the way we do resonance is we take a lone pair and we drop it down. Okay, so this is the second criteria that we discussed sort of. And once we do this, our next resonance form is going to be double bond between these two, single bond between these carbons, and now a double bond between carbon and oxygen. The oxygen should have two lone pairs. Okay, and overall no formal charge because we started with one negative and one positive. They combined, so overall no net charge, no formal charge on that structure. So these are the three resonance forms for this molecular species. Okay, the species that we have. So now if you compare these three and if you try to evaluate you know, which one's a major contributor, which one's a minor contributor, what you notice is that carbon with the positive charge is missing its octet in first structure. Carbon with the positive charge is missing its octet in the second structure. Whereas in the third structure, every atom has a complete octet. So based on that, we can say that this is a major contributor to the resonance. And similarly, the other thing that you can look at it is the formal charges. Notice how also in this third structure, we've minimized the number of formal charges. Okay, the first structure had 2 formal charges. Second structure had 2 formal charges. The last structure, there's 0 formal charge. So that also makes it a major resonance form. So that way we can use the octet rule, you know, figure out if the octet's complete and formal charges to predict which one's a major contributor. Since we have these resonance forms, let's also just review resonance hybrid. We will do a few more examples, but let's just review resonance hybrid quick here. Okay, if we have to draw a resonance hybrid for these resonance forms, okay, we're going to start by drawing the skeleton that does not change, and that is the sigma bonded framework. Okay, whatever that is not participating in resonance. So we have 1 carbon, 2 carbon, 3 carbon, and then an oxygen. So you have 2, 3, and then oxygen. This much does not change throughout all the resonance forms. Now, if you look at, you know, maybe let's label some of these carbon atoms. So 3, and then the oxygen, we have 1, 2, 3, 1, 2, 3. Label the molecules if you have to, you know, but again, I think I'll say try to get comfortable, you know, so if you can do this mentally, that would be the best. But if you look at all the structures, there is one structure, there's a single bond between 1 and 2, carbons 1 and 2, double bond and double bond. So overall, there's a double bond and a single bond. And since there are 2 double bonds between them and only 1 single bond, it's almost like a 2/3 of a bond. Yeah, not 1.5, but 1 2/3 of a bond. Okay, but you cannot differentiate between 2/3 and a half. So what we'll do is we'll basically show a dotted line here to say that okay, it is a double bond and then a single bond sometimes. The same is true for carbons 2 and 3. There's a double bond in one case, and there are 2 resonance forms where there is a single bond. So again, dotted bond. And between 3 and oxygen, there's 2 resonance forms with single bonds, 1 with a double bond. And so we'll show a dotted bond here also. And as far as the oxygen is concerned, it has 3 lone pairs in 2 structures, two lone pairs in one structure, but what is constant throughout is two lone pairs. So this oxygen will take two lone pairs. Okay, and now if you notice in this scenario here, there's a negative charge on the oxygen in two of the structures. So that negative charge is shown by using like a del negative. You can so say that there's a partial negative charge on the oxygen atom, and carbons 1 and 3, they have a partial positive charge. But in fact, that is shown over here. So if you want to, you can show this del positive and del positive, so that there is a partial positive at those positions. But overall, this molecule is basically, it should add up to no charge, because the major contributor has no charge on it. Okay, so overall, it's going to add up to like no charge between these structures, because again, notice that the oxygen has negative charge on two structures, and these carbons have negative positive charges on only on one structure each. So that basically cancels out. So the resonance hybrid, I think a true resonance hybrid for this can be shown just like that. No charge overall, because those charges would cancel out. So that would be a resonance hybrid for that molecule. Okay, so I think that was a video on how you assess the relative importance of various resonance forms for a molecule. Okay,